So yeah, Instagram stores over 1 billion photos and videos every single day. Can you even imagine the database infrastructure required to handle that kind of load?
1 billion? That's mind-boggling. It's one thing to hear the numbers, but another to really grok what that means for their engineering teams. It's not just about storage, is it? It's the read and write speeds, the indexing, the backups, everything.
Exactly. And if you think about what happens when it all goes wrong, imagine Instagram going down during the Super Bowl. The chaos, the memes about Meta's engineering skills, the impact on their ad revenue. That's where database sharding comes in. It's not just a nice to have, it's an existential requirement.
Okay, so let's break it down. For listeners who might be less familiar, what is database sharding in plain English? Why is it so critical for platforms at Instagram scale?
Think of it like this. Imagine you're running a pizza restaurant. At first, you have one oven. It's fine when you're only making a few pizzas an hour, but what happens when you suddenly get orders for hundreds of pizzas? The single oven becomes a bottleneck, right? Database sharding is like adding more ovens. You split your database into smaller, more manageable pieces, shards, and distribute them across multiple servers. This allows you to handle more requests in parallel, improving performance and availability.
Okay, the pizza analogy makes sense. But how does Instagram actually decide which data goes into which shard? That seems like a really complex decision. Is it random?
That's where the shard key comes in. The shard key is a specific column in your database table that you use to determine which shard a particular row of data belongs to. For Instagram, a common approach is to use the user ID. All of a user's data, their photos, videos, followers, etc., would be stored on the same shard. This is beneficial because most queries are user-centric. When you open your Instagram feed, the app only needs to query a single shard to retrieve your data.
Okay, I see the logic. Keeping user data together minimizes cross-shard queries, which would be a performance killer. But doesn't that mean some shards will be much hotter than others? What happens when a celebrity with millions of followers posts a photo? That shard is going to get hammered.
Here's the crazy part. That's exactly what Instagram had to solve. They realized that a simple user ID-based sharding scheme would lead to uneven data distribution and performance bottlenecks. They call these hot shards. To solve it, they introduced a concept called directory sharding.
Directory sharding? That sounds like something out of a fantasy novel.
It's actually pretty clever. Instead of directly mapping user IDs to shards, they introduced an intermediate layer, a directory, that maps user IDs to shard IDs. This allows them to dynamically rebalance the data across shards as needed. For example, if a celebrity's shard becomes too hot, they can move that user's data to a different shard with more capacity. The directory is then updated to reflect the new mapping.
So it's like having a dynamic routing table for data. That sounds incredibly complex to manage. What happens when the directory itself becomes a bottleneck? Is that sharded?
Another great question. Yes, the directory itself needs to be highly available and scalable. Instagram uses a distributed key value store to manage the directory, and they replicate the data across multiple servers to ensure high availability. They also use caching extensively to minimize the number of lookups to the directory.
Okay, so even the system that manages the sharding is itself distributed. It's turtles all the way down. But let's talk about another challenge, consistency. If data is spread across multiple shards, how do you ensure that all shards are in sync? What happens when a user updates their profile information? How does that change propagate across all the relevant shards?
That's where distributed transactions come in. When a user updates their profile, Instagram needs to ensure that the changes are applied consistently across all the shards that store the user's data. They use a technique called two-phase commit to achieve this.
Two-phase commit. Isn't that notoriously slow and prone to failure? I thought most modern systems tried to avoid it at all costs.
You're right, two-phase commit can be slow and complex, but Instagram has optimized its implementation to minimize the overhead. They also use techniques like optimistic locking and eventual consistency to improve performance. The key is to understand the trade-offs between consistency and performance and to choose the right approach for each use case. For example, updating a user's profile picture might require strong consistency, while updating the number of likes on a photo might be okay with eventual consistency.
So they're strategically relaxing consistency guarantees where it makes sense. That makes sense. It's all about understanding the specific requirements of each operation. Can you give me another real-world example of a company that uses sharding at scale and maybe a different approach they take?
Absolutely. Look at Uber. They use sharding extensively to manage their ride data. Given the sheer volume of trips they process every day, a single database would never be able to handle the load. They shard their data based on geographical regions. All the ride data for a particular city is stored on the same shard.
That makes sense geographically. It's probably a good bet that most queries are localized to a specific city. But what happens when someone takes a really long trip that crosses multiple regions? Does that require cross-shard queries?
Exactly. Those cross-region trips are a challenge. Uber handles them by using a combination of techniques, including data replication and distributed transactions. They might replicate the trip data to multiple shards to minimize the need for cross-shard queries, or they might use distributed transactions to ensure that the trip is recorded consistently across all the relevant shards.
So the trade-offs are similar, latency versus consistency. It sounds like choosing a sharding strategy is a really complex balancing act. What's the biggest mistake engineers make when implementing sharding?
Let's see. The biggest mistake is thinking about sharding too late in the game. Many companies start with a single database and only consider sharding when they're already experiencing performance problems. By then, it's often too late. The data model might not be well suited for sharding, or the application code might be tightly coupled to the single database. It's like trying to add lanes to a highway after it's already gridlocked.
So it's a foundational architectural decision that needs to be considered from the very beginning. It's not something you can just bolt on later. What about the operational overhead? Doesn't sharding dramatically increase the complexity of database administration?
Absolutely. Managing a sharded database is much more complex than managing a single database. You need to monitor the health of each shard, rebalance the data as needed, and handle shard failures. That's why automation is key. Instagram, Uber, and companies like Netflix invest heavily in tooling to automate these tasks. They use configuration management systems, monitoring tools, and automated deployment pipelines to manage their sharded databases at scale.
So you need to be prepared to invest in operational tooling and automation. What are some concrete things a software engineer can do today to prepare for a future where they might need to implement sharding?
Here are 3 things. First, design your data model with sharding in mind from the beginning. Think about how you would partition your data and choose a shard key that will distribute the data evenly. Second, decouple your application code from the database. Use an abstraction layer to access the database so you can easily switch to a sharded database in the future without rewriting your entire application. And third, learn about distributed systems principles. Understand the trade-offs between consistency, availability, and partition tolerance, the CAP theorem. This will help you make informed decisions about your sharding strategy.
So it's about being proactive, not reactive, thinking about sharding as a potential future requirement, even if you don't need it today.
Exactly. Think of it like planning for retirement. You might not need it today, but you'll be glad you started saving early.
That's a great analogy. So start saving for your database retirement today.
That's right. And remember, sharding isn't just about scaling. It's about building a resilient and adaptable system that can handle whatever the future throws at it.
Well said, Parth. That's all the time we have for today. Thanks for tuning in to The Code Architect.